Thank you. Uh, Thank you, Travis. Good morning, ladies and gentlemen. First of all, I must thank Realization for inviting me over here. This is the third consecutive year that I'll be speaking in Project Flow Conference. A few more years like this, and I'll probably get the Long Service Award. But I must thank Sanjeev for inviting me over here. And all the people, I also must thank Ajay Kapoor because whatever I know of about critical chain today is all because of the hand-holding I got from Dr. Ajay Kapoor, and I'm really grateful to him. I'm also grateful to the Realization team. I keep on complaining often about different things, and I've never seen them getting irritated or angry. I mean, what stuff are these guys made of? I don't know. And of course, the conference organizers, as well as Norma, Chloe, and Wakar. I mean, I probably create a lot of fuss whenever I come over here with all my requirements, all my calls, but I've never seen them getting angry or irritated or anything, and they've always helped me. So thank you, everybody. In the first half today, what we looked at was General Zettler talked about was very global, the GDP of the world and the GDP of US. And then we talked about some systems. Now, this is going to be much more ground level stuff, very focused in a particular area. And what you were seeing over here is a finishing mill upgrade in Tata Steel. Now, for those of you who have seen the Goldratt satellite program on operations by Eli Goldratt, he gives an example of a steel plant where cast steel slabs are rolled into plates of different sections. Now, this is exactly the mill that he's talking about when he's talking about that. So as we go through, we will we'll go through that presentation. In Tata Steel, we started applying critical chain in maintenance and sustenance projects in December 2005. From there on, we've applied critical chain project management techniques to 10 mining projects, 9 projects in blast furnaces, 29 projects in steel melting and casting, 29 projects in rolling mills, both hot strip mill, cold strip mill, as well as wire rod mill. These are different types of mills. 11 projects in cinder plant, 12 projects in power plants, over 100 major shutdowns or turnaround projects in the last 5 years. Right. Now, let me just give you a project brief on what this project is all about that I'm going to drill down further. This is the mill that we are talking about. We have cast slabs. Liquid steel is cast into slabs of 210 millimeter thickness and wide about 1 to 1.5 meters, 11 meters long. And then these are heated in another furnace to about 1100 degrees centigrade, that's about 2000 Fahrenheit. And then they're rolled into something called a roughing mill, where 210 millimeter thickness is brought down to 30 millimeter thickness. And then there's this finishing mill over here, which is a continuous mill. There are 6 stands, and this 30 millimeter thick plate is reduced to anything between 1.6 millimeter to 16 millimeter thickness. And this whole operation happens for a particular slab in 1.5 minutes. And this is the final product that we are talking about. The project we are talking about over here that I'm going to elaborate on is a project worth about $90 million US, out of which we already have 2 reheating furnaces. We would be putting a 3rd reheating furnace. And the roughing mill and the finishing mill upgrade, which costs about $65 million US. Now, this requires about 1 year of preparation. This required about 1 year of preparation. followed by 11 days of execution in the field where the current plant would not be producing anymore for 11 days. Now, and by doing this, we would increase our output from 3.25 million tons per annum to 4 million tons per annum. A 0.5 million tons per annum increase results in about $200 million per year of revenue. And each day the plant is out, it's not producing, we lose $2 million per day from the current. I mean, we produce, before this happened, we were producing around 10,000 tons per day out of this plant. We would be producing 12,000 tons after this. So what was needed in this project was $65 million getting installed in 11 days, 30 task managers, 5 external agencies, 300 workmen, 4 different countries, 15 experts, and there are some internal shops like assembly shop and motor repair shop and so on and so forth. Now, just to give you an idea about Tata Steel hot strip mill and the group, the Tata Steel group is a 140 years old group with a turnover of 60 odd, right now I think it's about $70 billion. The steel unit, and Tata Group is into everything from cosmetics to steel to mines to automobiles and so on and so forth. The Tata Steel Group is the 8th largest steel producer in the world with a turnover of $33 billion. Now, where I come from is Tata Steel India, which is located in a place called Jamshedpur in the eastern part of the India, in the country. And this part has probably some of the richest iron ores available in the world. I mean, it's literally pure iron ore that we are talking about over here with 67%. I mean, if you actually break up Fe2O3 into their molecular weights, then you would probably get 67% iron, and that's what we have over here. So a very beautiful place to have a steel plant. And of course, the coal, I mean, the other thing that is required in a steel plant is coal. So we have coal mines all over this place, and we have iron ore mines all over this place, very close to each other. Our last year's turnover was about $6 billion. We own our own raw materials, and we are famous for corporate social responsibility. Now, this is the process flow at hot strip mill. You have the mines. We own our own mines. We have our own mines. That gets produced through different processes through the blast furnace into something called a hot metal, which is more of a cast iron. That gets processed further into steel melting, that's LD1 and LD2, that's steel melting, which gets further rolled into different shapes. And this is the mill that we are talking about, where this particular case was implemented. Right now, to talk about the mill, we are talking over here of 2 furnaces, reheating furnace. The input is something like this, 210 millimeter slabs that we I talked about, and the output is something like this, 1.6 to 16 millimeter thick sheets. We have 2 reheating furnace. This $90 million of expansion would result in a 3rd reheating furnace. This is the roughing mill over here, in between. This one doesn't seem to work. Okay. Anyway, followed by the finishing mill, and then there's a cooling table, and then there are coilers where the material gets the coil form. Now, in the past, when this mill started, it was a 1 million ton mill per annum. We improved it to about 2 million tons, and then there was gradual improvement by product mix, by increasing average coil weight. We got it up to 2.87. Then we had this electric upgrade, which got us to 3 million plus. Now, when this electric upgrade happened, that was the first year we had applied the critical chain in this plant over here. And then it remained stable at around 3.27 million tons, and with this investment, it would go up to 4 million tons. Right. Now, why this investment in the first place? Now, as General Zettler was saying that India is growing at a phenomenal rate. Now, steel demand is going at 12% growth rate, average growth rate. Now, that's crazy. I mean, in 6 years, you need double the capacity of the country than what we have today. Now, but then there are a lot of socio-political reasons for which a greenfield expansion is very difficult. So, what you need, a brownfield field expansion is much easier. And so, it made a lot of sense to increase the capacity of this mill rather than put up a greenfield expansion. Now, this shutdown would take 11 days for this upgradation to happen. And the throughput loss would be around $2 million per day. So, if I can manage to save 1 day, that's $2 million for the company. And what we needed was also, in order to fulfill the annual business plan of production, there's a measurement for all these mills which is known as net operating hours, which is availability. And availability, we needed an availability of 6, 7, 7, 8 hours for the entire year. Now, this could be achieved, and there are regular stoppages of the mill, I mean periodic stoppages of the mill, that's necessary. One of the things that would help us achieve it is 9 days of shutdown. Right, what was the scope of shutdown? I am just focusing on the finishing mills. I have showed just 5 stands over here because that is where the changes happen. The 6th stand did not have any changes. So, what we were changing were the gearboxes and the F3 motor, and there were a lot of dependencies within this. I will talk about the dependencies as we go along. Now, when I talk of these gearboxes, each one of them weigh about 45 tons. So, you just can't pick them up and take them somewhere and then put a new one in. Right, now, just to give you a scale of things, give you an idea of scale of things, you know, the roughing mill that we are talking about, you see these 2 people standing over there, and that's the size of the mill. Now, this is the mill part. To support these, the drive part is behind a wall, and that had to be taken apart and sent back, some to repair shop and others to just take it away and put back new stuff into it. And these are the finishing mills that we are talking about, and these are some of the motors. Now, these mills require to exert a load of about 40 meganewtons. The motors driving them put together require something like 30 megawatts of power when they run. Now, the city that I belong to, Jamshedpur, consumes somewhere around 550 megawatts in all, including all other industries. There are lots of industry over there. All our industries put together is around 550 megawatts, and these few mills put together consumes about 10% of the whole power. So, that's the size we are talking about over here. In terms of motor change, what are we looking at? We are looking at, first remove the covers, and this is all of 30 megawatts. So, the entire weight is about 60 tons of this motor. Remove the cover, take away the bearings and the couplings, take away the field bodies, and then the armature, and then put them back again. Right, and this had to be done in 65 hours. Why in 65 hours? I will talk about it as we go along. Now, so what does the thing stands like? You know, the motor part was being done by Teco Westinghouse from Britain. The gearbox part was being done by SMS Demag of, I mean, these are people who are very common, contractors or suppliers who are very common to steel plants, was being done by SMS Demag in Germany. And the automation level was being done by Convert team of US. So, you had different countries, and getting all of them together was a big problem. Now, when the plans got made, people thought this is the way the project would happen, and this would take 11 days. Now, obviously, in this there is commissioning of 54 hours. Now, you really do not know what is going to happen during commissioning. You can't really predict that. So, you can't do much about it. So, this is gone. When we got the people together, Teco Westinghouse and SMSD, we realized that this job can only happen after this. Otherwise, there would be major alignment issues. So 11 days, no way. Now, this is where it comes in. In order to get it to 11 days, the only way we can do it is if the motor work can be completed in 65 hours. Then we can bring it back. So if you take that out, then all that we are left off with is uncertainty. Now that's dependency, and the other one was, the entire place where all these motors are there is a room of about this size, maybe twice the length, and you have all these motors, and with all these motors you can't put in some extra cranes. There's only one EOT crane in the motor bay on top. Now this crane had a load distribution in terms of loading of crane had a load distribution like this. Now obviously it gets booked for 7 days, but in between there are days where you need twice the crane capacity. Now this was a big issue, and there wasn't enough space to actually get in another crane. And we are not talking over here of small size cranes, we are talking over here of cranes which can take in 50 to 60 tons of weight. So mobile cranes really can't get into that space. Right. So this was the other problem in terms of crane capacity. Now, while preparing this presentation, I was just wondering if I were to make this presentation before the shutdown, then I wouldn't be showing this slide. Because this was a completely unrelated project. Some pipeline being brought in, this is about a 3-kilometer long pipeline, that's 2 meters in dia. And this is a new gas pipeline that would be needed for the third furnace. And for this shutdown to be up, the last part of this pipeline was connecting it to some of the lines of our current furnace, right? So unless that connection is made, there's no way that we can start the current furnace's operation. And if that doesn't happen, it doesn't matter whether the mill starts or not, anyway the plant can't start, because you need the furnace slabs to be heated. Now, how did this interfere? I'll talk about it later. And of course, there were 6 companies involved, 4 countries involved, a lot of disciplines, all the disciplines that you can think of. And there were these efficiency driven practices. Now, even with 4 to 5 years of experience in critical chain, if I need a resource and I don't have it, I'll try my level best to ensure that when I have it, I'll keep it. So what strategy did we evaluate and adopt? The first thing was to evaluate whether this project is actually feasible in 11 days. For that, we had to change the F3 motor during shutdown. But then we also had to change F2 motor at some point of time. So this was a good opportunity. We took up F2 motor and we wanted to check whether it could actually be replaced in 65 hours. Dismantling took much less than what we had estimated, but then alignment and all took much more than what we had estimated. All put together, we could understand where are the pitfalls, what are the areas where we can get stuck, and there were obviously actions taken to prevent it from happening. The other was crane as a resource. Now, my experience says that you might say, okay, at the end of the day, it's 71% of the total duration. But then during commissioning, anyway, you don't need the crane, so that goes off. But even at 71% of any resource capacity booking, it's very, very high to manage. So what we did was we staggered the crane usage in such a way that we could evenly distribute it over a certain, we first did an early start, early finish. That's what you saw in the previous graph. We looked at late start, late finish, and we realized that there was day 4 where there was very less crane usage. So we managed to stagger some tasks into that area. Then the big one, that we had to change the rules. Now, in terms of crane usage, the rule that we put in place is only one man decides where the crane will go. Now, that was not too difficult. The other part was release the crane when you don't need it. Now, we had to go to the extent of creating certain punishments for people that if I have the crane and I am not using it, then I am in trouble. So, if I am not using it, leave it. Doesn't matter if it's idle, but leave it. Just don't keep the crane to yourself. The other part was the tool matrix that you see over here. And of course, in terms of the supervision plan, it was 24/7 working. So, accordingly, the supervision plan was worked out. The other part, of course, the last was release control of work. Now, as Dave also said that for all technicians and mechanics, you give them a screwdriver and a spanner and they will find something to open and close back again. Now, that's very true all over the world. Now, this is release control is a difficult thing to implement. In fact, I think that's the most difficult thing to implement while implementing critical chain. Now, one thing the rules were simple. F3 motor work would only start once F3 gearbox is over. If F3 gearbox is not over, then F3 motor can't start. If people are sitting idle, they are sitting idle. The second one that we put in place was F4 gearbox and F2 both need to be sent to the shop. Now, what we realized while allocating crane was that I can work on only two gearboxes at a time. Otherwise, I would require more crane capacity. So, that's something we implemented over there. And the third was that F3 motor work can only start once RM motor work is completed, roughing mill motor work is completed. Now, with these rules we started off, and the interruptions that we came across, the first interruption was itself on day one. Now, when you see the trend graph of this project, your instant reaction will be, how come the entire project is in green, it never went to red. Now, let me tell you this, we had nightmares during the day, but fortunately we could resolve all these nightmares within that same day, so the curve remained in green. There were these old foundation bolts for the gearboxes. Now, these foundation bolts, there were 20 odd of them, and we had to replace them to put the new gearboxes, because the new gearboxes were of higher capacity. So, we had got 20 bolts. Now, these 20 bolts worth over $1 million. So, that's the size of bolts that we are talking about. And when we tried to take out the old bolts, they wouldn't budge a millimeter. Now, after 3-4 hours of trying to take them out, at only one bolt, forget the rest of them, we said, okay, let's take out only one and see what it takes. We actually gave up, and at that point of time we thought that did we take a wise decision in trying to upgrade this mill any further? We woke up some Germans in SMSD and then got them on the drawing board and asked them that, can these bolts last with the new gearboxes? So, they got back to their calculation. They kept on telling us what all tests to be done on these bolts so that the new gearboxes could be fit. So, all this happened within 5 to 6 hours, and fortunately the old bolts would work fine. So, we let them remain over there and fit the new gearboxes on the old bolts. That way we actually saved a little bit of time. Had we taken off the old bolts out, then we would have had to redo the foundations. So, we saved a little bit of time over there, but then what really worked over here was quick decisions. The other one was roughing mill motor job took a long time, much longer than what was expected. Now, there was something interesting that happened. On day 3, when I went there, the electrical fellow comes to me and says, is SMSD on time? I said, why? What's your problem? You do your job on time. So, his reaction was, no, I want to know whether they are on time, because I have to start F3 motor. So, I said, are you on time on RM? So he said, no, I'm late. So I said, don't worry about it. Continue your work with RM, start on F3 motor, doesn't matter whether SMSD has finished or not. Start on F3 motor only when you have finished RM gearbox. So that decision over there really helped. The third place where we had a major interruption was, and we had no clue about this, I mean this project was not even in the focus. This pipeline at this point over here, this particular tower is TW4, tower 4. Now when we were monitoring this project, after 1 or 2 days, we realized that at tower 4 the job is stuck. Now whenever we asked these people that what happened to tower 4, they would say, oh, see tower 6 is ready, 10 is ready, 8 is ready, everything is ready, so why are you worried about tower 4? Now day 1 that happened, fine. Day 2, exactly that same thing happened, that they were not ready to talk about tower 4, but they were ready to talk about everything else, and where the progress was very good. So at the end of the review meeting, I asked the chief of this hot strip mill, I said, why don't we just take a walk and see why is this tower 4 stuck? And we went there, and both of us started laughing when we went there, because there was this restroom, workers restroom over here, this has got shifted now. There was this restroom exactly at the place where this foundation was supposed to be built in. And tinkering around with restrooms is major industrial relations problem. So then we realized that, and the other part was, there was the shop over here, so the line had to bend, this needed a bend over here. We couldn't bend it too much because anyway gas flows and liquid fluid flows are very complex subjects that designers don't want to talk about. So we immediately escalated the matter right up to the president of the workers union. And we went to him and said, look here, this is the story, just give us some time, we'll make a temporary arrangement and we'll shift the toilets. The designer was put in, because you see once you have these restrooms, then you also have the underground sewage line and water lines and so on and so forth. So that, so the whole foundation had to be redesigned, and that's why this is the curve of trend chart of this particular project, which is an unrelated project, where over here it got stuck, it was going up, and then it went straight back because we had to redesign the stuff. But then everything recovered over here. Don't worry about this vertical line. Towards the end, they were actually ahead of the finishing mill project. So they had to wait over there just to make those final connections to the current furnaces. Right, in terms of results, the biggest satisfaction that we derive from implementing critical chain is in most of these organizations where you have an operations staff and you have the maintenance staff, and if the engineering staff comes in, then it's a real mess. I mean, they spend more time fighting rather than doing projects. One thing that good that happened about implementing critical chain in all projects in Tata Steel was the fact that there was major harmony among the entire team, and for the whole team it was the project which was important and not individual groups. The other big gain that we have seen in implementing critical chain in Tata Steel is, in the 5 years of critical chain implementation, I mean, it's very difficult to make a correlation or establish a correlation, but the fact is, I mean, you know, steel plants are pretty infamous for fatality. All over the world it's like that. So we have DuPont as a consultant on industrial safety for us, grooming us as on safe practices as well. So recently one of these DuPont consultant made a comment that I don't know what you all are doing with these shutdowns. 5 years, so many shutdowns across the plant, not one fatality, not one accident. So you all must be doing something good. Now I don't know whether it's because of critical chain or not, but it could be because once you start having low WIP into the system, then you have less activities going on at any point of time, so less chances of accidents. This, of course, the results of this particular project was 9 days was the target. 11 days was the original plan. We achieved it in 8.8 days. The trend chart is all in green, but then if you also notice, it's also gone to that minus time over there. So at some point of time, we actually had to update, saying that no, we can't do it in this time, within this time. As a result, last year we finished at 3.65 million tons. This year we will finish at around 3.87 million tons, and next year we will cross 4 million tons. In terms of NOH, net operating hours or availability, these are the benchmark levels, and we are at 6690 last year. So that's slightly better than, we didn't achieve our target, but then we are slightly better than the best in the world. In terms of savings, those 2 days saved us $4 million.